So we're going to talk about solving an initial value problem in a first order differential equation. And as with an antiderivative, we often need a particular rather than the general solution for the first order differential equation. All right? So the particular solution satisfying the initial value condition can be represented as y of x sub 0 equals y sub 0, which is the solution for y equals y of x. Whose value is y sub 0 when x equals x sub 0. The graph passes through that point x sub 0, y sub 0 in an xy plane. So, considering this, we can define a first order initial value problem, which I'll represent as IVP when I need to say initial value problem, is y prime equals f of xy which must satisfy y of x sub 0 equals y sub 0. So we're going to do an example now, and we're going to show that this function, y equals x plus 1 minus 1/3 e to the x, is a solution to this first order initial value problem given the initial condition y sub 0 equals 2/3. So in order for us to do this, we have to recognize what we're looking at. The equation dy dx equals y minus x is a first order differential equation. I'll just write DiffEQ with f of xy equal to y minus x. So we'll deal with this in two sides, and we'll think about having a left side. The left side is my derivative, dy dx. And the derivative is going to be d dx of that original function, y, which is x plus 1 minus 1/3 e to the x. And if we simplify that, we get that dy dx, the derivative of x is 1, the derivative of 1 is 0, and the derivative of 1/3 e to the x is, we're going to have minus 1/3 e to the x. Thinking about the right side, my right side of the equation is y minus x. And what is y minus x equal to? Well, the y, which was originally given, our original function, is x plus 1 minus 1/3 e to the x. So all of that right here This represents y, and then we still need to take away our x. And simplifying that, we'll get y minus x equals the same thing because those two x's cancel out. I've got 1 minus 1/3 e to the x. And so because the left side and the right side are the same, we can check here and say, well, does it? And we will prove that the function satisfies the initial value condition because y of 0, which is x plus 1 minus 1/3 e to the x, that being my original function, if I evaluate that at x equals 0, at y of 0, if I plug 0 in for all of those, I end up with 1 minus 1/3, which is 2/3. So this satisfies my initial condition of having that ordered pair 0, 2/3. And if we went just a teeny bit further and thought about, what the graph actually looks like, we get this exponential function for y and it has that ordered pair at 0, 2/3.